So, my name is György Salló, and I'm a senior solution architect at Qamcom Research and Technology Central Europe. And in the next 15 minutes, I will present to you a solution to a practical problem. So, what is the problem? So, instead solar panels, energy production is affected. So, affected means here diminished by a series of factors. It can be improper installation, which is quite common when you have to install thousands of solar panels. Then some panels are misconnected or not connected. There can be some damages caused by hail. You can see on the picture that it's quite damaged. Bird droppings, it's quite funny, but it seems common. But of course, any other type of dust and accumulated dirt can affect also the power of the solar panels, and also the shadowing effect of the vegetation. These parts, well, usually are maintained rarely. The grass is not cut, and the grass can grow, and the bushes can grow, and this has an effect on this. And what's more, these panels are usually connected serially in strings, and one faulty panel can affect the solar energy production of the whole string. And well, the less energy production is missed revenue, and this can be for larger parks in order of millions or tens of millions of forints annually. Okay, so obviously a proper maintenance is needed, but the area of large solar parks can be as much as 100 hectares, and can contain tens of thousands, or, well, the parks above 100 megawatts, hundreds of thousands of panels. And this is absolutely a daunting task for human supervision or inspection. And what's more, not all the types of force are visible by the human eye. So for these panels have to be disconnected and measured, and of course this is not feasible for tens of thousands or hundreds of thousands of panels. So what is our proposed solution? Well, inspection and image acquisition by drones, and we acquire infrared images and RGB images. So why infrared images? Because most of the solar panel faults manifest themselves as excessive dissipation of heat in certain region of the panel. So obviously this is more visible in infrared images. Well, after that we do some image processing and do automatic detection of faulty panels, and we do site reconstruction to localize the exact geocoordinates of the faulty panels. Okay, so how do we do the image acquisition? We use a commercial drone and two cameras, an RGB camera and an infrared camera, and careful flight plan has to be prepared, because as we can see later, the flight parameters can affect very much the outcome and the results of the analysis and image processing. So what is our pipeline which we put together? So we have the drone tremor images. We segment the solar panels from the environment. Of course, we also have to track the panels, because the same panels appear in several frames or images, so we identify them and track them across several images. We rectify the images, because obviously the drone flies at a certain, and the panels can be seen at a certain angle as parallelograms, not as rectangles, so we have to rectify them to be rectangles. We do some image preprocessing, we do automatic fault detection, After that, we visualize the results and do manual verification and post-processing if needed, and we automatically generate a PDF report about the distribution of faults and some statistics on this. Yeah, and of course we do a solar plant reconstruction as well in order to identify the exact geo-coordinates of the faulty panels. If the customer requires this, we do orthophoto reconstruction as well, but this is optional, nice to have, it's not needed for the task. Okay, so how we do the panel segmentation and tracking. We do the segmentation from infrared images using a well-known convolutional neural network, mask RCNN. It is tried and tested, and it works pretty well in our case. For the RGB images, we don't use a deep learning network, but we use classical machine vision techniques like edge detection, and where we cannot find the edges, we use homography with the infrared images, where the panels are already segmented. For tracking, we identify ORB features on the images, basically key points on the panels, and using these key points we can identify and track the panels across multiple images. There on the right side you can see the results of the segmentation of the infrared image and the RGB image. Okay, how we do we transform the segmented panels to rectangular shape? We use a quite well-known technique, structure from motions, to reconstruct the camera poses of the drone. From the multiple camera poses, we establish the panel center and corner point coordinates by triangulation or multi-angulation, because of course we have multiple camera poses, and we use a parallelogram rectangle homography to rectify these parallelograms to rectangles. And of course we do a site reconstruction, which is the determination of the geolocation of individual panels. On the right side you can see the results of the site reconstruction of the individual solar panels. Above you can see the results of the segmentation, and as a result we have multiple infrared images of one panel and multiple RGB images. Okay, so how do we do the fault detection? So we use several techniques here. One is a deterministic algorithm for finding bypass diodes. You can see on the far right side of the slide, it's 1/3 of the panel is hotter, or 2/3 of the panel is hotter than the other part, and we can detect this with classical computer vision methods. We do image processing for this with histogram equalization to increase the contrast of the images. Yeah, the other type of very common faults, it's the so-called hotspots, which can have multiple causes, and these can vary in shape and size and can be present in various parts of the panel. And for this we trained an object detection model to identify the hotspots, namely YOLO. Precisely YOLO 8 was used for this, and with quite good results. And as a last thing, we use temperature-based filtering for identifying critical faults. What we mean by critical faults? well, if the maximum temperature of a panel it differs with more than 5 degrees Celsius from the median temperature, then we mark the fault as critical fault. Okay, so we developed a tool for visualizing the results and for manual inspection. Here you can see the screenshot on the right of the tool. So we can see one panel in different color schemes and different contrasts, and we use this mainly for detection and removal of the false positives. This is quite important because usually when a panel is marked faulty, then the operators are not trying to repair it or whatever, they simply replace it with a new one. And if a healthy panel is replaced with a new one, then this is not the outcome that the solar park owner would like, and neither would we. Okay, what were the challenges which we faced? A couple of them, of course. Well, as I mentioned before, sensitivity to drone flight parameters, flying height, flying speed, rotations of the camera, which should be avoided, the abrupt rotations of the camera. Well, the flying height is also important because these panels are on the images, the segmented panels about 75 per 40 pixels, and one hotspot can be as small as 7 by 7 pixels. So it's quite challenging to detect on these. Different panel types require different methods and models to be trained. So we had to retrain the mask RCNN model for the monocrystalline panels. They are polycrystalline type of panels and monocrystalline type of panels, and the monocrystalline type of panels has a bus bar in the middle. So the old model detected this as two panels, which obviously is wrong. Another challenge is that the faulty panels have a small percentage from the total panels, typically less than 3%. And we had to overcome this challenge. We, of course, did image augmentation, did artificial hotspots on good panels, but maybe we should consider using an image generation technique to produce artificial faulty panels. Well, tuning the object detection model detection threshold also was very tricky. It turned out that this had to be set quite low in order to detect all the hotspots that we would like to detect. Well, there are hotspots like anomalies which are not faults, and this is challenging even for the humans to discern. So this is an area which has to be explored more. And last but not least, there is a domain shift between the data coming from different solar parks, meaning that one model trained on a solar park does not necessarily perform as well on the data of another unseen solar park. But as we have now data from multiple solar parks, and we combine the data from multiple parks for training, we achieve good results on an unseen park data as well. Okay, what are the results? So the automatic fault detection, the precision is above 96%, which is of course is important for having as less false positive as possible, and the sensitivity is between 94 and 99%. depending on the park, and this means that we detect the faulty panels at this percentage. What are they delivered for the customer? As I mentioned, we have a report, executive summary, detailed report with the images of the faulty panels. And what is interesting, we also deliver them a CAML file, which is an abbreviation for keyhole markup language, if anybody has heard about this. It's actually a kind of XML file, and you can overlay its data to a map, for example, Google Maps. And this is quite convenient for the serviceman, because they can download this CAML file on the mobile phone or on the tablet. And as you can see, they can visualize where exactly the faulty panels are and where they have to go to replace them. Okay, so what further development we are working on? So as you can see, well, we can detect the hotspots on the panels on the right side, and we can see the corresponding RGB image, but from the infrared image we do not see the cause of the hotspot. And well, this can be only some dirt, and it's need only panel cleaning and not replacement of the panel. So actually, if we train a model to classify the causes of the hotspots, then we can recommend also actions for the owners to what to do. Panel needs to be cleaned, or vegetation has to be cut. You can see on the upper picture that the vegetation is shadowing the solar panel. We also want to have an interactive website for analysis for customers, and we are working on a power loss estimation tool where the power loss of the solar park can be estimated based on different input data like plant specifications, solar irradiation level, temperature data, and of course the logs of the inverters, from which we can get the actual power production. So thank you for your attention, and if you have questions, I will be around for a while.